All right. So good morning. We wanted to take this time to take a look at chapter 2, the chemistry of life chapter. You've got a 30-point multiple choice quiz, we'll call it, on Thursday over chapter 2. So we're just going to take some time this morning to see if anybody would like to go over any aspects of chapter 2. I did print off the study objectives. I'm assuming a lot of you guys probably did the same and have referenced those various objectives as you sort of started to study and prepare for this, because we did not take formal time out of lecture, as you know, to talk about chapter 2. Since we had that expectation that anybody coming into AMP1 has had at least high school chemistry, and many perhaps maybe haven't even taken some of our introductory chemistry courses at JCC. So I have no preconceived agenda in terms of how this is going to go. So I'm going to just open the floor for questions or comments. What's causing you questions, confusion, etc., etc., etc. Who wants to be the first?
We need to know like the different reactions between the chemicals.
Well, to the extent to which the book describes, let's see, on page,
Like on 53.
right, 52 and 53, section 2.3b, they describe decomposition reactions, synthesis, exchange, and reversible. So I would just know basically what the differences are between those. And I think that's fairly easy to answer, because you can just, look at, for example, on 53, where they talk about decomposition reaction, they say, look at AB and then an arrow to A plus B. You're breaking down AB into the two constituents. I mean, it's really very logical when you think about it. Reversible reactions have arrows that go in both directions, meaning that depending upon the concentration of the different compounds, we might go from left to right or right to left. So yeah, Ariel, I would know the 4 basic reactions: decomposition, synthesis, exchange, and reversible. So that if you saw on the quiz, for example, question number 4, it says, the following is what type of reaction? And I have A plus B yields AB. Could you identify that as a synthesis reaction?
Okay.
Yeah. Or if I said Na plus Cl yields NaCl, would you recognize that as a synthesis reaction?
Mm-hmm.
Yeah. And I think that might actually even be, objective number 10, isn't it, on the sheet? Yeah. Other questions? A good way to prepare for this quiz, as I've mentioned, is to go through the objectives and develop sort of a study guide, if you will. That's an excellent way to prepare for that quiz. I tried to be as specific as I could in developing those objectives. And I think go ahead.
What about like on page 59, like all those pictures, like do we have to know any of those? Like
No.
how many, like the unsaturated fats, acids, and all that stuff?
Yeah, you don't need to, I'm not gonna ask you to draw out stearic acid, or anything like that. No. But if I gave you any of those 3 listed at the top of that figure 2.18, could you tell me whether it is a saturated or an unsaturated fatty acid? That's a question I could ask you. And if I did, how would you tell whether you're dealing with a saturated or an unsaturated fatty acid? That you need to know. So how do we
But
tell? By looking at the chemicals.
There's HO, like in this acids, like it's HO to the carbon and oxygen, double oxygen.
Well,
then-
all of those three have that left-hand functional group you're describing, right? The carbon double
Yeah.
bonded to the O2 or to the O and then an OH group. So that won't tell you whether it's saturated or unsaturated, will it? Well, look in the molecule, look in the straight chain carbon regions where it's carbon to carbon to carbon. What's the difference there?
The bonds.
Yeah. What's different about the bottom one there, the linolenic
It
acid?
has 2 sets of double bonds to the carbon.
Exactly. And because you have a double bond between those carbons, that means that those carbons are restricted in terms of how many hydrogens they can bond with. In other words, just one. If there was a single covalent bond between the carbons, you can get 2 hydrogens bonding, right, to each of those carbons. So you're exactly right. Unsaturated fatty acids have 1 or more double bonds between the carbons somewhere in the molecule. That's how you tell unsaturated from saturated. Look for 1 or more double bonds between the carbons. Between the carbons. There's always going to be a double bond between a carbon and an oxygen on the left-hand side there. That's part of what's called the acid group. But you got to look in the long carbon to carbon, what they call the straight chain part of the molecule. Now, in this example, where we're combining those 3 different kinds of fatty acids, shown in pink and yellow and orange, to the glycerol there on the left in yellow, what kind of a reaction is that? Is that a catabolic reaction or an anabolic reaction? Anybody know? You should know this. Is it anabolic or catabolic? If you don't know the difference between the two, I guess you wouldn't know the answer, but you should know the difference, because we talked about that a little bit. Now, that wasn't specific to chapter 2, I guess, but we did talk about anabolic and catabolic with regard to metabolism. What are we doing? Are we building up or breaking down here?
Building.
Right. Therefore, it's anabolic, right? And we talked about a special name of a reaction, right? That describes anabolic reactions. It's listed there in the figure caption. It says dehydration synthesis, doesn't it? Yep. So that's an example of what we were describing last week in lecture. So when we make this unsaturated fat there at the bottom, what makes that an unsaturated fat is the fact that you have somewhere in those 3 fatty acid components at least 1 carbon to carbon double bond. And of course, that's in the bottom orange one, the linoleic acid part of the triglyceride. Now there's 2 there, right? But all you need is 1 to make that whole fat molecule unsaturated. And that means that at room temperature, that's going to be a liquid, because saturated fats are solids at room temperature. Things like lard, animal fat, that's a saturated fat. And that's because if you look within the molecule, you'd find no carbon to carbon double bonds. But if you look in what do you got in your cabinet at home? Some kind of an oil, safflower oil or olive oil, that's an oil because you have basically unsaturated fats. So that was a long answer to your question. You don't need to know the chemistry of the molecule in terms of having to draw it out, but you ought to be able to recognize unsaturated from saturated fats. That you should know. And again, that I think is referenced somewhere in one of the objectives. Yeah, 16. Now, as I look, for example, at table 2.7, lipid functions, you don't have to memorize that table. That's not necessary. I think that table 2.6, I would be familiar with what the difference is between a monosaccharide, a disaccharide, and a polysaccharide. Right? I think I would know basically what that means. You'll begin to learn some of these examples of monosaccharides and maybe some di and maybe some polys. We've already talked about glucose a little bit in class last week. And we'll talk more about it tomorrow. Remember, this was the fuel molecule that your cells are going to be breaking down to make energy. But you could actually break down any of those different carbohydrates and get energy, because ultimately you could break it down into monosaccharides like glucose. Sucrose, for example, the things we use for cooking and baking, that is a disaccharide with glucose and fructose combined. Di means two sugars. Starch, like you find, let's say, in pasta or potato, that's a poly. It's a really important storage molecule for plants. And that's made up of glucose. Hundreds and hundreds of glucose molecules all linked together. Other questions related to the objectives? Let the objectives be your guide. Keep in mind, as I just look at the objective sheet, that there are some sections here related to enzymes and ATP, for example, that you don't have to worry about for the quiz on Thursday, but we have begun to talk about that, for exam 1. We get into a little bit of discussion of things that we've talked about in cellular respiration and ATP cycle leading up to that topic that they introduce in chapter 2. I'd be able to recognize an amino acid from a simple sugar like glucose. I'd be able to recognize those. I'm not going to ask you to draw anything out, but if you saw glucose on the quiz, could you recognize it as glucose? If you saw an amino acid on the quiz, could you recognize it as a building block of proteins? What makes an amino acid unique? Well, they talk about that. There's an amino group and there's an acid group, they call it. So you do want to be able to recognize molecules, the building blocks of proteins and carbohydrates and lipids. Come on, there's got to be some questions out there. I guess I should have assigned everybody they needed to come to this review session with at least one question written down.
What about like let's see, on page 65, like the membrane transport, and all that.
Okay, so this talks about some functions of proteins. We have talked a little bit about this as it relates to the membrane back in, what was it, chapter 3, right? So that, I would say, is something that you're studying for the, for exam 1 material in chapter 3. So those listings of membrane functions might actually be the very same ones as listed on page 81 of chapter 3. So I guess I would try to get comfortable with some overall functions. Yeah, if I asked you, like, give me 2 functions of proteins, could you do that? You don't have to memorize all 7 of the bulleted items necessarily. That's not the goal here. But I think it's good to begin to have ideas about what these different molecules do, what their roles are in the cell. We've talked about membrane transport. We've given some examples of that. We've also talked about recognition, how some cells use these markers, these proteins on the surface of the cell membrane to recognize other cells. Remember the example I gave you was, if I'm a white blood cell, how do I know whether to attack and kill this cell and not this cell? Well, the way I do that is I have membrane proteins that will literally connect with other proteins on other cells, and that allows me to recognize those as part of the body. We call them self cells, or non-self cells, like, say, a cell that's been invaded by virus, or a cancer cell, or a mutated cell that could become cancerous. So surface marker proteins are really important in recognition, cell-to-cell recognition. Just think of the immune system as a good example of that. But it's not a function of trying to memorize all of those and be able to regurgitate. But I would have a good idea of general functions of proteins.
Okay.
The more you get exposed to this, the more we talk about this, the more you're going to be building your knowledge base on proteins. I mean, we've talked about enzymes quite a bit. Enzymes are proteins. What do? Well, they help reactions go faster, more efficiently. If you just stop and think about it, I'm sure you can come up with a couple examples of what good proteins do for us, because they have a lot of functions in the body. Yeah. Ariel, you're the one leading the discussion today. You got some good questions. I appreciate that.
You're welcome.
And I know others do. They're just afraid to ask, probably. Do not wait until Wednesday night to start preparing for this quiz on Thursday, which obviously you haven't done because you're here today. So you're wanting to do well on the quiz.
Well, we need to know anything about Marie Curie.
Marie Curie. I do say in all of these chapter objectives that you should look at the deeper insight sections here. So they do describe her there on page 43. So I think you should get into the habit of reading those and being somewhat familiar with what they're talking about there. So I would read that. I would, just get a general sense of what her role is in science. You don't have to memorize dates or necessarily, that she won a Nobel Prize in 1903 and another one in 1911, which is really quite interesting. I think actually, if I remember correctly, the display case there on the second floor of the Science Center, there's some information about her. I remember reading or seeing recently. I think it's still there. Yeah, she was a really amazing woman. I mean, we're talking about, you know, a person that lived back in the 1800s, early 1900s, and her work on radioactive isotopes, unfortunately, ended up killing her. I mean, it's a really amazing, somewhat sad story. But what a brilliant woman. Two Nobel Prizes. I mean, that's just amazing. So, anyway, long answer to your question. I would be familiar with these deeper insight boxes. They're scattered throughout the chapters. There's usually like maybe, I don't know, it depends how big the chapters. It might be 2 or 3 per chapter, something like that, maybe.
What about like the pH scale and all that stuff?
Yeah, I think you ought to be familiar with the pH scale. Let's go and look at that. That's on page 51, right?
Yeah,
Yep.
51.
Yeah. So you ought to know that it goes from 0 to 14. And that 7 right in the middle is considered a neutral pH. It's not an acid, it's not a base. And that as you go from 7 toward 0, the materials, the solutions become more and more acidic, right? They'd be defined as an acid. As you go from 7 on up to 14, those, of course, would be considered alkaline or basic solutions or compounds. For each integer change in pH, like from say 5 to 6 or 10 down to 9, you know, a one integer change represents a 10-fold change in the hydrogen ion concentration. What that means, for example, is if you look, let's say at, let's look at an example there. Let's look at egg white and pure water. You see that the pure water has a pH of 7, and egg white, of course, has a pH of 8. So what that says,
10 times more acidic.
no,
basic-
not 10 times
basic.
more acidic. No, what that means is that pure water has 10 times the hydrogen ion concentration as egg white does. Okay, that's all that says. This has to do with hydrogen ion concentration. Typically, when we measure pH, we're measuring it in hydrogen ion concentration. The more hydrogen ions, the more acidic. The less hydrogen ions, the more alkaline. What if we compared coffee to pure water? What's the hydrogen ion concentration difference? How much more does coffee have than pure water? Again, we're talking a 2 integer change. What does that equal in terms of hydrogen ion concentration difference?
20.
No. It's not 10 times 2, which I can see where you'd say that. It's 10 times 10. 10 to the second power, which is what?
100.
Right, 100. What if we compared, let's say, egg white to coffee? What are we talking there? How much more hydrogen ion concentration do we have in coffee?
1,000.
Right, 10 to the third. 10 times 10 times 10. Yeah, good. Now, another way of saying this is that egg white has, when we compare it, let's say, to pure water, we can also say that egg white has 10 times the hydroxide ion concentration as pure water. Because even though we typically express pH in hydrogen ion concentration, there's also another ion called the hydroxide, OH, with a little minus charge. I don't mean to confuse you or to muddy the water here at all, but we can talk about pH in two different ways, really. We can talk about hydrogen ion, which is what most people do, or we can also, or we can talk about hydroxide ion concentration, because it turns out the more hydroxide ions you have, the more alkaline or basic the solution is. So whether you have less hydrogen ions or more hydroxide, it's the same idea. If you have more hydrogen ions or less hydroxide, it's the same idea. At neutral pH, the concentration of the two ions is equal. And this is getting beyond the scope of what you need to know. But that's basically what's going on. At pure water, pH 7, neutral, you have the same concentration of hydroxide as you do hydrogen ions. As you shift toward 0 from 7, then the amount of hydrogen ions go up and the amount of OH goes down. I think I can point this out to you by showing you a diagram now that I think about it. So hang on a minute. Let me see if I can find this diagram that I'm envisioning. Here we go. Let me share this diagram with you. I think it'll make more sense. Share screen. Okay, do you guys see the pH scale there? Do you see it? Okay, so I really like this. I don't know why they didn't. Well, this was in the old book, so to speak. And I can provide you with this PowerPoint, and no problem. I'll just free it up on Blackboard. But here's 0, right? Here's 14. There's 7. And then what we're looking at here in red is the hydrogen ion concentration, and in blue, here's the OH hydroxide ion we talked about. So look at pH 7. The red and blue are the same quantity, if you will. As we shift to the left, look what happens to the red. It gets higher, more. What happens to the blue? It gets less, doesn't it? So at a pH of 3, for example, which you would define as what? Acidic or basic?
Acidic.
Yes, acidic. That doesn't mean there aren't hydroxide ions contributing to its alkalinity. It's just that there's more hydrogen ions. So by definition, if there's more red than blue, it's acidic. If there's more blue than red, it's what?
Basic.
Basic, right. So milk of magnesia, 10.5. Yes, it's defined as an alkaline or basic solution, but is there hydrogen ion in that? Yes, there's some. There's more hydroxide though, and that's what makes it alkaline. I really like this visual. I hope maybe, does it help you guys kind of visualize the difference?
Mm.
Yeah, I like that. So I'll free up this chapter 2 PowerPoint from the previous textbook, and I'll put it next to chapter 2 from Saladin, and you can look at it if you want, or check out this figure. So that's as much of pH scale as you need to know. 0 to 14, 7's neutral. Anything below 7 defined as acid. Anything above 7 defined as base or alkaline. And that between an integer change, right, 7 to 5, 7 to 6, or 3 to 2, or what have you, represents a 10-fold change in hydrogen ion concentration. Or you could think of it as hydroxide too, yes. But technically, the definition of pH is the negative log of the hydrogen ion concentration, if you want to know the math, which you don't need to know. So
I don't have
go ahead.
questions. I don't have any more questions. That's all. Those are all my questions.
Okay, great. How about other folks?
Well, we need to know the dehydration, synthesis, and hydrolysis reactions, like that diagram that it shows on page 56.
Okay, let's take a look. 56. So this is what we talked about in class the other day. I would say not for the quiz on Thursday, no, but for the first lecture exam, yes, because again, we specifically talked about these, I think it was last Thursday or Tuesday, I forget what day it was. So I would not worry about that for the quiz Thursday, but I would make note that we did discuss this for the
Yep.
first lecture exam. Yeah, more in chapter 3, I think we got into it, didn't we? Or maybe it was chapter 4.
I think it was chapter 3, I want to say.
Yeah. I just am getting my chapters mixed up. But we did talk about it in some detail, didn't we, the other day? Yeah. So we'll put that in the first exam and not on the quiz on Thursday. So I do say, for example, in the carbohydrate section, you should be familiar with, some of the common simple monosaccharides, as well as some of the disaccharides and the polysaccharides. So we talked a little bit about that earlier, excuse me. So know what glycogen is. How does it differ from glucose? Well, glycogen is a polysaccharide. Glucose is a monosaccharide. So you see some examples on page 57 and 58 of mono, di, and polysaccharide. So again, if you were to see, let's say, lactose there in figure 216 on 57, if you were to see that lactose molecule on the quiz, could you recognize it as a disaccharide? The answer should be yes. Get those 2 rings. Carbohydrates have ring structures, but they make them up.
Is hydrogen the weakest bond that there is?
I'm not a chemist, so I would maybe be wrong if I said yes, it is the weakest chemical bond there is. It's the weakest chemical bond of those that chapter 2 gets into. So yes, I would consider it as the weakest bond you need to think about or be familiar with. There's covalent, there's ionic, and hydrogen. I think those are the 3 that chapter 2 discusses. Let's see, where do they talk about that? That must be, well, they actually also talk about van der Waals forces, but we're not going to worry about that one. We're going to focus our attention on ionic, covalent, and hydrogen. And is everybody comfortable with the difference between those 3 kinds of bonds? What's the difference? Do you know? And we can talk about any one of those 3 or all 3.
We just go over all 3 of them.
So let me see if I can find the diagram here. Okay, so here we're talking about a single covalent bond. So in the case of covalent bonding, we have sharing of valence electrons. What are valence electrons? Does anybody know what that means, the term valence?
The electrons on the outermost shell.
Very good. Excellent. And if you don't know what that means, then you need to go back, okay? And you need to understand a little bit about atomic structure, basic atomic structure. Go back in earlier sections of chapter 2, and they talk about the importance of valence electrons. So exactly what you said. These are the electrons in the outermost shell of the atom. And so here in this example, we're looking at two hydrogen atoms, and we see that each has a single valence electron, as illustrated by the blue circle in the orbit, if you will. Well, it's not really an orbit, it's an energy level. You also have to understand that the first energy level can hold a maximum of 2 valence electrons. When you get to the second and the third, then we jump up to 8 possible electrons that could be held in those energy levels. And we can go out to the 4th and 5th and 6th and 7th, and I don't know how many, depending upon how complex the molecular or the atomic structure is of that atom. And the numbers of valence electrons, I think, increases as you get into bigger and bigger, more complex atoms. But we're going to worry about basically the first 2 energy levels. So just remember, first energy level can hold a maximum of 2, and the second can hold a maximum of 8. If they can fill their outermost shells with a maximum number possible, which would be 2 or 8, then we create a stable chemical situation, basically. But if it's not full, then these particular atoms tend to be reactive. And so, again, what we've got here are 2 reactive hydrogen atoms, each of which has 1 valence electron. Now, how many would each like to have, if it could, to be stable? Answer is 2, right? That's the maximum number in the first energy level. So what's going on here on the right-hand side is these 2 hydrogen atoms sharing their valence electron with their neighbor. This achieves a full outer shell, and we form hydrogen gas, H sub 2. That's the chemical formula. This is the molecular formula, showing a little line here between the 2 hydrogens. This line, solid line, as a covalent bond. So that is what's going on with regard to covalent. I can give you another example. Let's see. Let's go to this one, the double covalent bond. What's going on here? Looks more complicated. Well, it kind of is. So we're looking here at an oxygen atom, right? Here's a carbon, here's another oxygen. If you look at the valence of oxygen, it has a valency of, let's see, 2, 4. If you look it up in the periodic chart, 8, so let's think it's got 4, 5, 6, it has a valence of 7. I wish they would have given us just the individual atom of oxygen. They don't do that here. Let me go to the other chapter PowerPoint and see if they do. All right, let's do this. Yeah. Okay. We'll go back. Do you all see the double covalent bond diagram? Yes, no, maybe. Are we out there?
Yes.
Okay, thanks. So This is going to be a little confusing because they don't show the individual atoms before they interact with one another. Here they're interacting. And basically what this means is that rather than sharing a pair of valence electrons, they're sharing two pairs. That's what the four here are. This is represented as a double covalent, like an equal sign between the carbon and the two hydrogens. This allows for outermost filling of the second energy level. So if we were to look at oxygen, for example, how many valence electrons do we have now once they've started to share their outer two pair? We've got 1, 2, 3, 4, 5, 6, 7, 8. That's full. Same would occur for the other oxygen on the opposite side. What about the carbon sandwiched in between? What's the valence number here? We'll count them up. 1, 2, 3, 4, 5, 6, 7, 8. That's also full. If we achieve, again, full outermost energy levels or shells like we've done, that creates a stable scenario. And what we've created in this instance, of course, is carbon dioxide, which you're exhaling as we speak. And so rather than a single pair like we had between the hydrogens to make hydrogen gas, we shared two pairs or four between the carbon and the two oxygens. This is a stronger bond, the double covalent, than the single covalent is. But just remember, regardless of whether it's single or double or even triple, you're talking about sharing, equal sharing of valence electrons, such that the outermost energy levels become full and stable, and then these are happy campers. Now that's the 8th grade version of covalent bonding. Equal sharing of valence electrons. This is different than ionic bonding. And let's see, where is that introduced in the chapter? Okay. Here's ionic bonding. The classic example they always give is between a sodium atom and a chlorine atom. Now, what I like about this, that they didn't do in the covalent bonding, is they showed the scenario, the atomic structure of the elements before they interacted. So now I can show you, okay, look at sodium. What's the total number of valence electrons in a sodium atom? We're out to the 3rd shell now, right? You see 1 here, right? Valency of 1. What is the number of valence electrons in the chlorine atom?
7.
Right,
7.
7, exactly. Now, if the book had done the same thing back here with this diagram, you would have seen oxygen having 2, 4, 6, 7 valence electrons and carbon having 4. And they didn't do that, so fortunately it became a little difficult to try to describe this. But here we can see what's going on. Now, we are not going to get sharing when one has 1 and one has 7. That's just not going to happen. So what's going on? Well, we see the black arrow indicating sodium is going to donate its outermost valence electron to chlorine. So this is not an equal sharing. This is I'm going to give you, I'm going to be very thoughtful. I'm going to give you my outermost valence electron because I'm a nice guy. And then, as we see down below, we make something called sodium chloride, which is a salt, right? Look at the valency now of sodium, the sodium part of the sodium chloride. Full 2nd shell, right? What about chloride? Full 3rd shell, right? Both filled their outermost shells. That's stable. We're happy. But in so doing, what do we know about this electron? What is its charge?
Minus.
Right, -1. Electrons are negatively charged. Protons are positively charged. How about neutrons?
No charge.
Right, neutral. I'm assuming you know that, all that stuff. So when we transfer this negative charge from the sodium to the chloride, that gives the chloride portion of the molecule a -1 charge. This is -1 understood. I don't put a 1 here, but you have to understand it's 1 because there's 1 transfer of a 1 electron. If you count up the total number of electrons now, there's 18 minus charges and there's 17 plus charges. That gives you a difference of -1. What about the sodium end? It has 11 plus charges, 10 minus charges for a difference of +1 understood. So when you form sodium chloride in an ionic bond, the sodium ion, it's called, and it's called an ion because there's a charge, is a +1. The chloride ion within the sodium chloride has a -1. And you say, well, so what? That's important because when you take a look at what exists within a sodium chloride crystal, and let's see, where can I show you that? Okay, again, this is from the other book. Here's the sodium chloride. Here's the +1 of the sodium. Here's the -1 of the chloride. Here we're looking at an artist kind of three-dimensional conception of the sodium chloride crystal.
We don't see, I can't see it.
Okay, thank you for telling me, because I don't know if you don't tell me. How about now? Okay. Yeah, sometimes when I go flipping back and forth between, it doesn't show up for you guys. So thank you, Ariel, for telling me that. So here we're looking at the same idea. This is from the other textbook. And so here's the sodium, here's the chloride. Here's the artist sort of sketch as you peer into that crystal, because you know salts are crystals, right? Now, are you going to see green and blue balls? No, no. This represents, the green represents chloride, the blue represents sodium. If you could peer into that crystal, and maybe there are some electron microscopes that allow you to see the individual ions, I'm not sure. But what do you know about unlike charges? This is basic physics. You should know this from 3rd grade. Unlike charges, what?
Cancel each other out.
No.
Don't they like attract each other?
Yeah, right. Unlike charges attract. Like charges repel. Don't you remember as a kid having a magnet? 2 magnets. And if you push them closer together, sometimes they click together. And if you flip the magnet, turn it and do it, what happens? It pushes away. Haven't you ever done that as a kid? Yeah. So same idea. Unlike charges attract, like charges repel. So within this crystal, you've got a bunch of chloride ions shown here in red, negatively charged, surrounded by positively charged sodiums because of the unlike charges. Another way of saying that is surrounding each sodium, positively charged, are negatively charged chlorides. So that's what holds this crystal together. It's the unlike charges of the separate sodium and chloride ions in the crystal. Now, what's an easy way to break those blue and red balls apart? It's not to hit it with a hammer.
The charge of one becomes the same as the other.
Well, no, my question is how do you break these blue and green balls apart if you wanted to separate them? It's so simple, you're going to say, oh, duh. How do you dissolve a crystal? Put it in water, right? So if you put sodium chloride in water, it dissolves. You know that. That would liberate those ions from one another. They would separate apart. There's nothing holding them together. The water dissolves via osmosis, kind of breaks those apart. So if you try to conduct electricity in that solution, you'll be able to do that because you've got these various ions floating around. So salts generally conduct electricity once dissolved in water. That's a trait of salts. Anyway. And then the hydrogen bonds, which is what started this whole conversation off, is the weakest of the three. All right, in order to explain these, I've got to talk about water. Water is a good example of how hydrogen bonds form. So let me look here and see if I can find water. Okay, tell me what you see here. Does it say figure 2.6? Yeah, okay. So earlier I was talking about the molecular and structural formulas a little bit. So when you see H2O written or CO2 written, you've all seen these. That is the molecular formula of the substance. It's what you're most familiar with seeing. These four are the structural formulas. They tell us, okay, in CO2, you've got these two double bonds, right? In water, you've got a couple single covalent bonds between the hydrogens and the oxygen. So this just tells you a little bit more about like the type of covalent bonds you've got, basically. So I want to look at water here. And as we've said, we're talking about a hydrogen here, two hydrogens really, sharing their valence electron with oxygen. And in so doing, all three parties are happy because they filled their outermost energy shell or energy level. Okay, I want you to expand your thinking a little bit now. Of these two elements, the hydrogen and the oxygen, which of the two is bigger? Do you know? Which has a more complex atomic structure? This may be an unfair question to answer, but maybe you can answer.
Oxygen.
Right. The oxygen is a much more complex atom. And okay, do you see the covalent bond? Okay, so here's a good example. Let's look at this water right here. You can see it's got two energy levels. It's got 8+ charges. It's got 8- charges because it's sharing here with the oxygens, or the hydrogens rather. And then here's the two little bitty hydrogens, one proton in the nucleus, one valence electron, but of course it's sharing again it with the water, so we create with the oxygen, so we create the water. So we talk about the oxygen here being more electronegative. What that basically means is that of these sharings that are taking place, right, the electron from each hydrogen is going to be more attracted to this end of the water molecule than the valence electrons will be here on the hydrogen ends. I'll say that one more time. Because of the higher electronegativity of oxygen compared to hydrogen, think of it as being more complicated, bigger atomic structure. It's exerting a greater tug on these shared electrons because it has 8+ charges here, and electrons are attracted, negatively charged electrons are attracted to the positively charged protons. So they tend to be attracted more to this end of the molecule. You have to remember these electrons are spinning around at the speed of light. They're not static, they're dynamic, they're spinning really, really fast. So when you look at how these shared electrons are being shared, yes, it's equal sharing, but it's creating this slight negative charge on this end and the slight positive charges on the hydrogen ends. So you get something that looks like this. Here we're looking at a model. Here is the oxygen in red. Here's the two hydrogens in white. Again, you can tell by the relative size of the circles, this is more electronegative, exerting a greater tug on the shared electrons. And because they're negatively charged, we tend to form this slight negative side here and a slight positive on the hydrogen ends. What this creates is hydrogen bonds between the water molecules. You told me earlier that unlike charges attract, right? We saw that in Ionic. Well, if you have a slight negative charge here on the red and a slight positive charge on the white of the adjacent water, you can kind of imagine where you might get a slight attraction force between those unlike charges. So that's what a hydrogen bond is. These dotted lines represent attractions between individual adjacent water molecules. Now, these are fleeting. They break and reform thousands of times a second because these water molecules are floating around in a liquid, right? Think of a glass of water. So they break, but they reform almost as quickly as they break. What this creates are some very special, interesting properties to water. The fact that you can take a glass of water and you can fill it up to a point where there's a slight film along the very top of the glass. Have you ever done this? It's really interesting. It's called high surface tension. Water has a high surface tension because of this, because of hydrogen bonding. Yeah. Now, if you continue adding water to the glass, it's going to overflow, obviously. But you can get to a point where if you get your head down and you look at the top of the glass, there's like this little oval film of water that's going to hang in there. You know, that's really cool. It's referred to as, again, surface tension. Water would not be able to do that without hydrogen bonding. Water would not be able to exist in 3 states simultaneously without hydrogen bonding: liquid, gas, and solid. Think about it. Water can exist in the liquid form. Water can exist in the solid form. Look out your window, snow and ice. Look up in the sky, that's the gaseous form. So water is really a really cool compound when you study its chemical properties. It's pretty amazing. All due to, at least a large extent, to these hydrogen bonds. So typically, as the name implies, hydrogen is involved in some way. It's usually between hydrogen and another electronegative compound nearby, basically. So these are weak. Another example of where you can find hydrogen bonds is in DNA. So let me see if I can find DNA here. Double helix. Okay, look here on the right-hand side. We'll talk about DNA coming up very soon in class. But you have double-stranded molecule, you all know DNA, double-stranded helix. Here we're kind of unwrapping it, looking at its chemistry. These dotted lines between the nitrogenous bases, A opposite T, C opposite G, those are hydrogen bonds. So hydrogen bonds hold that double helix together. So while they may be rather weak individually, collectively, they give water all these really cool properties, and they provide structure to that double helix of DNA. If you didn't have hydrogen bonds, those double helices would fall apart. They're kind of like rungs of a ladder. If you use the analogy of a ladder, you know, you step up the ladder, the steps are the hydrogen bonds. Cut away the steps, the ladder falls apart. Okay, how about time for one more question, because we're getting to be an hour, I think, now. Any last minute questions?
We don't have like any like other thing like quiz tomorrow. We're just doing lecture, like
Correct.
going over the main stuff.
Correct. Okay, well, I will see you guys tomorrow morning then, and I'll post this on Blackboard probably sometime in the next hour or two, in case you want to go back and watch it or whatever.
Thank you.
Okay, guys, thank
Thank
you
you.
for showing up. See you
Thank
later.
you.
You bet. Have a good day.